Hello, good afternoon, everyone. So let's start. First, something to announce. First, we don't have a quiz this week. We don't have a quiz next week, and then we'll have a final exam, which is a must-have exam, right? So please make sure you're gonna join in person. And if you need some accommodation, some of you might have request additional accommodation places rather than join the exam here. You probably need to start scheduling. And I have created the items online in the accommodation center. So if you could start, make schedule to make sure like there's enough room for you. Otherwise, it could cause some like chaos or problem. Extra accommodation. Yeah. I mean, if you have requested that, you should know that. But if you've never done that, it's fine. It's totally fine. Um, um, okay, so that's for the final exam. And oh, by the way, any question regarding the final exam schedule? Okay. Yeah. Again, it will be on April 30th from 3:30 to 5:30 on this room. It was scheduled by campus. It's not scheduled by us. Okay. Second thing is that someone asked about, okay, if there's any mock or practice for final exam. Yes, we have a released version in Canvas. Please start looking at it. We will release the answer case for that mock exam next week, but not this week. So we want to give you some time and room to practice by yourself first. And I think next Tuesday will be our final lecture. We'll walk through the problems in the mock exam, and hopefully that will help your preparation. Okay, so I think the remaining task will be just homework 6. Please make sure to submit assignment on time. And second, please take some time to prepare for your final exam. Any questions so far? Okay, great. So let us continue with the confidence intervals because this is probably the last important topic which is going to be covered in the final exam. We'll have a light introduction to the hypothesis testing, which will not be covered in final exam, but is to help you to give you a comprehensive picture about the tasks in statistics. But confidence intervals are an important topic because only when you know the confidence intervals would you understand why people are doing hypothesis testing and so on. Okay. So the motivation of the confidence intervals, as we have emphasized previously, is that we not only want or just a point estimate of whatever parameters of interest is not sufficient. Right? In practice, people want a more comprehensive quantification or estimate of the things of interest, like stock price, like precipitation. Those parameters are unknown. So the only way you can estimate them is to do some kind of measurements. You do some experiments and you observe the values. Say you rate the odometers, you get temperature rate or precipitation rate, or you look at the stock market, you look at the price, right? You have collected a set of random variables, their values, which we call a sample, right? And a realization represents one collection of the measurements over the random variables. Then we're going to compute some statistics over those random variables to get our estimate, right? So that is called statistics, right? So again, statistics is actually a function of the random variables from which you're going to observe the random experiments or whatever random phenomenon you are interested in. So when we say a confidence interval, we're essentially not just leveraging, say, let me use another color, not just using a statistics to construct a point estimate. Right? We're actually using this statistics to construct an interval. Okay? So we know that interval will contain a lower bound and an upper bound, right? So both the lower bound and upper bound will be some kind of statistics, will be some function of the random sample we measured or we observed from the real world. Right? That's why the confidence interval is also random. Right? So it's like this is your ground truth. You know it's fixed, it's constant. There's no randomness there, right? Like even a corn, you know there must be some ground truth probability that it give you heads up, right? It's not random, but you just don't know what exactly the chance. And what you want is that, okay, I want to estimate this chance or this probability of saying heads up, right? So what you can do, you just through these coins many times, you can view like every outcome as independent random variable. You collect the observations of those outcomes based on which you compute some kind of estimate, right? So this is called statistics, right? So now we're not only estimating a number to approximate this ground truth chance or probability, whatever, right? We're trying to construct an interval. We hope that this interval will have large probability to include this ground truth parameter we're interested in, right? That's the key idea, right? So that means from the random sample, from its realization, we're going to construct the two statistics. One is lower bound, one is upper bound. And then the interval is decided by this random lower bound, upper bound. And we hope that by giving any confidence level, which we call 100, 1 minus alpha confidence level, you're gonna cover the ground truth. Okay. So how do you construct that? The most commonly used, most interesting quantity of interest or parameter of interest will be mean of a distribution. Say, you have some random variables, right? You know they follow some particular distribution. And now I'm interested in what's the mean of this distribution, right? Like in Gaussian distribution, the mean will be just mean parameter, right? And in Bernoulli distribution, the mean is actually the probability. You see the heads up, right? So in many scenarios, we want to estimate the mean of the target distribution, right? And what can we do, right? When we collect the realization of a set of RID random variables, right? We're going to leverage the so-called central limit theory. So the idea is that, okay, no matter what the form of the underlying distribution, you enrich those RID random variables, and this average, which we call sample mean, right? Which we call sample mean, will approximately a Gaussian distribution. Based upon that, we can do some kind of like shifting and normalization of this sample mean, right? if we subtract the sample mean by the ground truth mu and subtracted by the variance, standard deviation divided by the square root of n, then according to the property of the Gaussian distribution, this transform random variable Zn will follow a standard Gaussian distribution. And then through this guy, we can construct a confidence interval. This is just a quick review. We're not gonna redo the derivation again. But the key idea is that, okay, if I can know for Gaussian random variable whose probability density is a standard bell curve, right? If we can find out the critical value, which we denoted as Z alpha over 2, right? This critical value means that, okay, the probability that this standard Gaussian random variable is bigger than this critical value is alpha over 2. That's why this critical value is indexed by alpha over 2. Right? Due to the symmetry of this PDF function, right? We know that the probability this standard Gaussian random variables less than or equal to negative of the critical value will also be alpha over 2. So that basically means like we have found a interval which is between minus Z alpha over 2 and Z alpha over 2 such that the standard Gaussian random variable Zn falls in this range will be 1 minus alpha. And because Zn can be represented as sample mean shifted by mu and divided and rescued by this guy, right? And you do some kind of like a equation arrangement, you can immediately get your target parameter of interest mu, which is between sample mean subtracted by critical value Z alpha over 2 times standard deviation sigma over square root n, and sample mean plus the critical value Z alpha over 2 times standard deviation skewed by divided by square root n will be exactly 1 minus alpha. So this is our confidence interval, which represents the level 100 times 1 minus alpha. Any questions so far? I hope everyone feels comfortable about this. Although right now you just need to be able to follow the formula here to calculate the confidence interval for any alpha. But we would like you to understand how this confidence interval is derived, right? So please follow what we previously discussed throughout the cluster and throughout the class to derive this confidence interval. Okay, so then we give some example like once you know the size of your sample, right? Your random sample, you know the variance of your random variable, and you know the sample mean, you can immediately construct a confidence interval according to any choice of alpha, right? So we mentioned that to get Z alpha over 2, this is pretty easy. You can find out some dictionary in most statistic book, or you can use a computer library like using R language, right? Using R language, you can just query this Z alpha over 2 by just one line of command. And if you can take a look at homework 6, we actually have given you the reference. Okay. So now we have talked about the case that when you know the variance of the random variable, you just don't know the mean. How are we gonna construct a confidence interval? the idea is simple. I just look at the sample mean, and then I'm gonna add or subtract it by a critical value z alpha over 2 times the standard deviation, which is square root of the variance, divided by square root of n. Right? And this guy is computed from standard Gaussian, right? And it is actually some internal properties from the standard Gaussian. Right? So now there comes a problem, right? What if you have no idea what's the underlying variance? When we know the variance, according to the large central limit theory, we know that, okay, Zn roughly follow a Gaussian distribution with mean mu and variance as the variance of the original random variable divided by n, right? Number of samples in your random sample. However, what if you don't know sigma, right? What if you don't know the variance or the standard deviation? How can we construct a confidence interval? Okay. Formally, so far the estimation of the confidence interval requires that we know the true value of the variance. However, the true value of the variance typically is unknown in practice. Like, for example, I want to know the temperature tomorrow, right? Do you know the variance of the temperature tomorrow? It's very hard, right? And I want to know, I want to infer the confidence intervals of the Apple's stock price, right? Per share. Do you know the variance? Or you don't know, right? And you even do not know whether it follows a Gaussian distribution or not, right? And most likely it's not a Gaussian distribution. And what shall we do in such a case? Any thought? Any heuristics or rules of thumb you can come out to address this issue? Again, we're going to assume, okay, although we don't know the variance of the underlying distribution, right? We want to estimate, right? But we do have a collection of random variables, ID random variables, which we believe sample from this unknown distribution. We're still using the sample mean of those ID random variables to estimate the mean of the parameters, right? Of the mean of the distribution, but we just don't know what's the variance of the distribution. So, what kind of idea do we have, like, to address this issue? Yes, exactly, right? That's a very good idea. So now that we don't know the true variance, but I have a set of samples, right? I know those samples follow the target distribution. Now, why not I just use the empirical variance from these samples to get some estimate of the variance, right? And we haven't talked before, right? How do we estimate the variance? Anybody recall? The empirical variance, unbiased estimation of the variance. Okay, so let's just recite this together, right? So the estimation of the variance, right? Or probably I can use this guy, right? sorry, sigma hat square, right? Is you're gonna divide n minus 1. Okay? And then we're gonna sum over the difference, the square of the difference between every sample and its sample mean, right? So that's called empirical variance, which we have introduced before. We have also shown this is an unbiased estimator. Right? What does it mean for unbiased estimator? Unbiased estimator means if you take expectation over this estimator, it is the ground truth parameter that this estimator approximates, right? Like you approximate the ground truth variance, right? And remember, this estimator is also a random variable, right? It's just a function of this n random variables, right? So if you take expectation over this random variable, it turns out to be exactly the value I'm trying to estimate. Then it's kind of unbiased. Everyone feels comfortable? Okay. So a natural idea will be, okay, so previously we know that if I have sample mean, and if you know the exact variance of the target distribution, then I know that, okay, I subtract sample mean by mu and divided by square root of sigma square over n will follow a standard Gaussian distribution, right? And naturally, through this guy, we can construct the confidence interval like z alpha over 2 times sigma times the square root n, right? So this seems natural, right? So now, although right now we don't know exact value of the variance of their target distribution, now why not we just replace the variance by the empirical variance, meaning that we replace the variance by its estimation from the sample. Right? It seems a very natural choice, right? Because we don't know what exact is the variance of the distribution, right? Let us just replace this variance by our estimation of the variance from the sample, and then use the same way to construct the confidence interval. This is a good idea, and it's a very natural and useful idea. But here's the subtle thing. If you replace sigma square by the estimation from the sample, then you cannot view this guy. So this guy now is rewritten as sample mean subtracted by mu and divided by the estimation of the variance from the sample divided by n, right? This guy will no longer follow a Gaussian distribution, even from approximation view. In other words, even from the central limit theory point of view, it will be too rough to view it as a standard Gaussian distribution. Instead, we need to seek for more accurate description of this statistics or random variable. Then what is this distribution? This distribution is called a student t distribution. Right. So the student t distribution, which usually simply abbreviated as t, right? It will take not only the mean, the variance, but also an extra parameter, which we call a degree of freedom. So don't ask what does it mean for degree of freedom. It is not scope of our class, but just keep it in your mind. There is an extra parameter which is called degree of freedom in the student t distribution. And in our case, once we subtract the sample mean by mu and divide it by the square root of the sample variance, the estimate of the variance from the sample, right, by n, then this random variables or this statistic, which we denote by Tn, will follow a standard student t distribution with degree of freedom n-1. So what does it mean for standard t distribution? It just means that the same, it is similar to the Gaussian distribution. It just means like you got zero mean, you get 1 as variance, but you just have an extra parameter which is called degree of freedom, which is n-1, and n is the number of the random variables in your sample. Is this statement clear? Any question regarding the conclusion here? There are just two distributions, right? Student t distribution, you can view it, well, this is out of scope, but I can tell student t distribution is kind of like infinite mixture of Gaussian distribution. So it's like if you draw a Gaussian distribution, a standard Gaussian distribution, it will be something like this. Sorry, my drawing is bad, but I want to say, what I want to say is that, okay, this is a Gaussian distribution. You got top. Sorry. You got relative taller top and a thinner hill. But if you draw a student t distribution with any discrete finite number of the degree of freedom, then it will look like this. Okay. Sorry, it's still symmetric, but it is just too hard for me to write a perfect symmetric. Something like this. So you see that at the top, at the middle, it is shorter. And the Gaussian is taller, but in the tail, it is fatter. It's thicker than the Gaussian distribution. This is called student t distribution. And interesting thing is that if you take the degree of freedom to infinity, then you can show that student t distribution will converge to a Gaussian distribution. So this is a very well-known result in statistics. Okay. So that means like Gaussian distribution is just a special case of student t distribution, in which the degree of freedom tends to infinity. But in normal case, like in Europe, in common cases, like your degree of freedom won't be infinite, right? It's just a finite. If it's finite, it just means it has a thicker tail and shorter head. Question? Okay, so now that we know when we replace the true variance by the sample variance, the empirical estimate of the true variance, then the statistics we constructed here follows a standard student t distribution with degree of freedom n-1. And similarly, if we want to construct a confidence interval, we can find out a critical value for student t distribution with this degree of freedom, right? So suppose this is a student t distribution with degree of freedom n-1. So what we can do is that, okay, we can still find the critical value for this student t distribution. It's not Gaussian distribution, it's student t distribution. And we denote the critical value as t alpha over 2 here. Again, this critical value means that the student t distribution the student t random variable Tn bigger than or surpass this critical value, the probability is alpha over 2. Right? It just means this part of area is alpha over 2. And similarly, I mean, because this is symmetric, right? You know that the probability your student t random variable Tn less than or equal to t alpha over 2 minus will also be alpha over 2. Then that means like, okay, Tn, the chance that Tn stays in between will be 1 minus alpha, right? So this is basically says that minus T alpha over 2 less than or equal to your standard student T distribution random variable Tn and less than or equal to T alpha over 2 will be just 1 minus alpha, right? But thing is that the critical value itself is different from the Gaussian distribution, right? Of course, because they have different PDF function, they have different curve. And we can imagine that, suppose this is the Gaussian distribution, right? The critical value for alpha over 2 will be a little bit towards 0, right? Why? Because it has a thinner tail, right? You're gonna need more span to achieve the same area, which is alpha over 2, right? That's why you're gonna see that the confidence interval from T distribution will be kind of wider than the confidence interval from the Gaussian distribution. Does it make sense? Right. Okay, let me repeat again, right? Because Gaussian distribution, its PDF has a thinner tail, right? So it's like this blue curve is ugly blue curve. It has thinner tail. And if you want to find the critical value for the same alpha, right, you're gonna to move this critical value further towards 0, right? So that you can make this whole area to be alpha over 2 as well, right? And on the contrary, for this fat, thicker tail T distribution, because the tail is fat, right? It's thicker. So it doesn't need that to so close to 0, right? It can be further away to achieve the same area. So that's why for the same alpha over 2, this critical value for T distribution is typically bigger than the critical value for Gaussian distribution. And you can double check this through R or whatever statistic book. And then, because through the T distribution, we can construct this interval, right? And Tn, as we know, is sample mean subtracted by mu, and then divided by the sample standard deviation by square root n, right? You just do some kind of manipulation. You multiply the denominator on both sides and then move sample mean to both sides. You can immediately get the standard, the confidence interval for mu. So you see that compared to the case that we know the variance, meaning that we really know the variance, right? The only difference is that, okay, first, we're going to replace the true standard deviation by the sample variance and square root, right? And second, we're going to replace the critical value of the Gaussian by the critical value of the student T distribution. And that's it. Questions so far? Everyone feels comfortable? Right? As long as you understand this logic, then calculation of confidence interval is straightforward. You just look at, okay, what's the sample mean? You check out online our library or whatever statistics book, you find out the critical value for the student t distribution. You calculate the sample variance and take the square root and divide it by number of samples. Then you construct the confidence interval. Questions? Perfect, right? And one additional intuition I want to add here is that if we compare the Gaussian and the student t, right? You see that the critical value for Gaussian is more closer to 0, meaning that T alpha over 2 is usually bigger than Z alpha over 2, right? So that means if you look at this confidence interval, for student T based interval, is usually wider than a Gaussian based interval. And this is also reasonable. Why? Because in the student T based interval, we actually have no idea about the variance, right? That means in this case, we have more uncertainty about the distribution. So that means you have a wider confidence interval, right? And for the previous case we discussed, right? Why can we use Gaussian distribution to construct confidence interval? Because we know the true variance, right? We know the true variance of the target distribution. We know more information than the case that we use student T distribution. That's why our confidence interval can be tighter, because we know more information. However, if we know less information, you have to make a larger confidence interval for the same confidence level. So here, we hope that you can also capture intuition from this perspective, and actually is very reasonable. Question? Okay, so again, from the slides from what we discussed, it is very simple for everybody to compute the confidence interval. But we hope that you're not only just using this as kind of like blind formula and calculate, through typing some command in our library and do some simple calculation. We hope that you would also understand how this confidence interval is derived, at least for variance knowing and variance unknown case. Okay, so so this is some kind of like a description of the T distribution. Although we don't want to make this course seems too intense, right? So here we just give a text description about student T. It is centered at 0 and a symmetrical heel shape, but it has heavier, thicker tails, meaning that it goes 0 slower than the normal. So if we look at, if this is Gaussian, and as a contrast, so student T will like this, right? So it moves, it goes to zeros much slower than the normal distribution. And however, when the degree of freedom gets large, the T distribution converge in the limit of the standard normal distribution. Right? And one last anecdote about student T distribution is how it is called. Right? It was invented by some guy like 100, more than 100 years ago. And he gave this name because he is some kind of employee. He don't want to make his boss upset. So this is called, he call it this student T. He doesn't call it teacher T. That's the only reason. But then they forms the convention, and after that, like people call it student T distribution. Okay, so for your convenience, right? You probably don't want to find out some old text, old statistic book and look at those. At least when I was an undergrad student, right? Every statistic book, in the end, in the appendix, there will be a table. There will be several tables, right? For Gaussian distribution, for student T, and for gamma distribution, for exponential distribution. And when you choose different alpha, what is their corresponding critical values, right? And right now, you don't need to do that. You can just access some online platform like R platform, and then you just type one line of command, right? You can collect the critical value for any student T distribution. And here, if you want to know what is T alpha over 2, this critical value, you can just in the interface, you just type QT. It's called quantile of T, right? And 1 minus 0.5 times alpha, and you give degree of freedom, which is n minus 1, and it can immediately give you the number. And hopefully, this will help you with the with homework 6. Okay, so let's look at a concrete example, right? If we go back to the Wasatch snowfall example we discussed in the last lecture, right? We want to know what is the amount of snowfall, right? And we took 40 measurements on the same elevation. And of course, we're going to assume this will be ID random variables, ID of the 40 random variables, right? But this time, we do not assume we know the true variance of the snowfall, right? And we just calculate the empirical variance from these 40 measurements, which gives us 34. And our sample mean still is 620. Then we can first check the critical value for the student T distribution, which is denoted by T alpha over 2. So here we can take alpha equals to 0.05. So we check out this value, and then we add or subtract sample mean by this critical value at 0.025 times square root of the sample variance divided by square root of the sample size. You get the 95% confidence interval. Question? Yeah, by contrast, right? Yeah, our previous example, we're assuming we know the variance, which I kind of forgot, but let me just randomly write down a number, say 36. Then we're going to construct the confidence interval by, you're going to still add or subtract the sample mean and plus or minus, right? And now you use the critical value for standard normal distribution. And you still use same alpha level, which is 0.05. So it is 0.025. Then times square root of true variance, which is 36, and over 40, right? And now, when we no longer assume we know the true variance, then we calculate sample variance. So you're going to replace 36 by the sample variance 34 here. Then you're going to replace the critical value from Gaussian to the student T, and that's it. Question? Yeah, and this will leave as an exercise for you guys to double check, right? So when you replace the true variance by the sample variance, you calculate the confidence interval, and what does the confidence interval look like? Right? You will see that actually the confidence interval will get wider, and this will be consistent as we discussed just a moment ago, right? But it will give you like more concrete sense. Okay, so let's rest for a few minutes, and then we're gonna start talking about hypothesis testing. Okay. Yeah, let's continue. So next, the next topic and also the last topic we're gonna discuss is the hypothesis testing. So don't worry, we're not gonna go very deep on this because this is a very confusing area. And when I was a undergrad, it took me quite a while to understand what's the meaning for this. And it's really, those p-value stuff, the significance level is always confusing. And plus, I mean, in the recent few years, people have started to realize that the abuse of this hypothesis testing actually is harmful for the science and engineering. There was like some Nature paper published a few years ago talking about if you abuse p-value, actually it doesn't give you any reasonable result. However, we still need to talk about this type of methods because it is really really useful and important. And just it doesn't mean like it can work, it can always work, right? But in most cases, doing some kind of hypothesis testing can give you some kind of like strong confidence that whether your assumption is correct or not. Right? So okay, so the hypothesis testing was mainly introduced by R.A. Fisher, who is kind of like modern founding father of modern statistics, and it started from a interesting experiment. It's called a lady tasting tea. Right? So there was a lady, right? There was a lady. Of course, this is some kind of friends of our statistic pioneer, R. Fisher, and the lady claimed that she could tell whether milk or tea was added first. Right? By the way, R. Fisher is a Briton, from UK. So they got like long tradition, like drinking hot tea, right, rather than coffee, right? And but there's some kind of like tradition that okay, you're gonna add some milk into the tea, right? But of course, you can first give the hot water. You can first add tea and then add milk, or you can first add milk and then add tea. And a lady in some party where R.A. Fisher attended claimed that she could tell exactly, for any given tea, right, whether the milk was added first or the tea. Right? So the problem is how do you gonna examine her claim? Right? How do you make sure, or in what kind of like confidence do you believe her statement is true? Then R. Fisher designed an experiment. He kind of like made 8 cups of tea, right? And 4 of these cups with milk added first and then tea. And the remaining 4 cups have tea added first and then milk. Right? And of course, he gonna mix those different types of teas randomly and make sure that the lady didn't know at all, right? At first, right? Before the testing. And then it presented these 8 cups to the lady, and lady kind of like tasted or look at whatever, and this were not recorded in the history book, right? But the lady successfully identified all 8 cups, like in terms of like whether tea comes first or tea added first or milk added first. Right? So now there comes a question. Right? Through this one single experiment, do you believe this lady really has this super capability to differentiate the order, right? Or it's just a random guess, but and she's just getting all right totally by luck. Yeah, let me repeat again, right? Larry Fisher randomly cooked 8 cups of tea. 4 of them were added with milk first and then tea. The remaining 4 added milk first and then add tea first and then milk, right? And then they probably do some kind of random permutation and then present them to the lady. And the lady actually did some amazing job, and she correctly identified exactly which cups have milk first and then tea, which cup has which cups have the tea first and then milk. And then based on this result, what conclusion can get? Right? Do you believe the lady does have some kind of like super capability, right? Which can, I mean, she can differentiate this order, right? Which is seems kind of like unbelievable for ordinary people, right? Or this is just by chance, and she's so lucky and she got a chance to correctly identify every cup of tea. This is an interesting question, right? So the key is that how are you gonna analyze this result, right? The result is there. The experimental results are here, right? And the question is that how do we analyze them? And based on this result, in how much confidence we believe, okay, this lady does have such a capability, and how much confidence we believe it's not, right? So this actually motivates the so-called hypothesis testing. Okay? So to analyze this, right, Ari Fisher first proposed a hypothesis, which is called null hypothesis. And in statistic terms, it's usually denoted as H0. So this null hypothesis just says the lady is guessing. So what does the null hypothesis mean, right? It means that if you don't expect any surprise, right? And what is the most boring, what is most by default assumption would you choose? And of course, most people won't be able to tell for a given cup of tea, milk comes first or tea comes first, right? So the null hypothesis here is chosen as the lady is just guessing. And then we have some experiments, right? We have done some experiments. The lady tasted 8 cups of tea and correctly identified those orders, right, for every cup. Then based on those results, let's try to find if there's any evidence that can reject our null hypothesis. And by rejecting means that can we find any evidence which can claim that, okay, our boring common assumption that the lady's guess is wrong, and she does have some kind of like superior and unusual capability. So then how do we do this, right? How do we find evidence to reject H0? So the idea or the method Fisher uses, which is also from the basic principle of modern hypothesis testing, is that, okay, let us assume our null hypothesis is correct. Let us assume, okay, the lady is really guessing. If the lady is just random guessing, I want to say, what's the chance that she can correctly and simultaneously identify all the orders for all 8 cups? Right? We can start with a very simple model, right? So under our null hypothesis, the lady actually just randomly chooses 4 cups out of 8 cups. I mean, 4 cups, but just means like, okay, she probably just random pick up 4 cups out of these 8 cups, saying, okay, these 4 cups are having milk added first, and then milk, and then tea, right? And then the remaining, of course, will be tea comes first, tea added first, and then milk. Right? And then we know if you random pick up 4 out of 8 cups, the total combination will be this combination number, which is 70, right? And you know that out of the 70 possible choices, there is only one. There will be only one case that match the ground truth in this experiment. That means if the lady really pick up those cups randomly, her success of correctly identifying the order for all the cups will just 1/70, which is approximately 1.4%. What does it mean? We did some analysis, right? Under the null hypothesis, we come out the probability or the chance that the lady give the correct guess is just the 1.4% chance. And what kind of implication of our analysis? Yes, exactly, right? That's the key, right? So imagine that, or this is actually fits our intuition and practical, our practice, right? If you just do 1 or 2 experiments, and for example, these experiments follow some like underlying distribution, right? You will not likely to see a rare event happen, right? And you will most likely to say what's the most commonly possible case will happen, right? And when can you see some rare events? You're gonna do this experiment many, many times, like see 1,000 times or even 1 million times until you could see one possible rare event. However, if just doing 1 experiment, you're able to see some event with very, very little chance. That means your basic assumption about that distribution might be problematic. That's the key idea of the hypothesis testing. So for this particular experiment, right, if our null hypothesis is correct, that is, she's guessing, then the probability of getting all correct is too low, right? That's too low, right? You're gonna try 100 times until you get once correct, but now you just try once, you get all correct. That's impossible in practice, right? In practice, by default, we're gonna assume it is not possible to succeed in just 1 trial. So we're gonna reject our null hypothesis. In other words, we don't believe the lady is just random guessing, because if she's just random guessing, it's hardly for anyone can guess all 8 cups correct in 1 time, right? So we're gonna prefer another hypothesis, which we call for which the lady does have some capability to differentiate the order of adding milk and adding tea. Question? So this, I mean, we kind of omit a more complex analysis, because right now we're just using a simple analysis for the null hypothesis, right? If you want to do it more rigorously, search on the Wikipedia. It's called R. Fisher's lady drinking tea, tasting tea test. he uses actually a much more complicated distribution to analyze this, right? But the idea is the same. The intuition is the same. If I want to examine some kind of hypothesis, we're going to first set up a null hypothesis. And this null hypothesis usually represents those uninteresting, most common, and by default explanation. Then we first assume the null hypothesis is true. And based on this null hypothesis, we come out some probability model. And then we'll look into our observation or our experimental outcome and trying to calculate the probability of the observed outcome. If under this null hypothesis, the observed outcomes actually lead to a rare event, then we should reject the null hypothesis. Why? Because if that outcome is that rare, is so unlikely to happen, how could it be possible to be observed or be captured just in one experiment? Then we're going to reject the null hypothesis. Then we're going to accept an alternative hypothesis. So this is called hypothesis testing. Question? I mean, this is a key idea, and this is a core idea, and no matter how kind of like a complex a hypothesis test procedure look like, and what kind of like a difficult or complicated distribution do they use, the key idea is always like this. Right? You're gonna first set up a null hypothesis, which represents any common uninteresting default explanation. And underlying this assumption, you're gonna make some probabilistic model. And you want to, when you use this model to explain your observation, your experimental outcome, you find out, wow, this is actually a rare event. Then that can kind of give you some flash warning. It gives you some warning message, because if your hypothesis, your null hypothesis is true, then your observation shouldn't be a rare event. It should be a common event. Okay. But if your hypothesis, but now even under your null hypothesis, your observation becomes a rare event. That means your hypothesis is problematic, and we should reject this null hypothesis and then seek for alternative hypothesis. Any question? Okay, so now let us give a formal description about the procedure of conducting hypothesis testing. So step one, we're going to formulate the so-called hypothesis. Right? So we're going to create a so-called null hypothesis H0, which, as we explained, it should be the most common used by default boring or interesting hypothesis like random guessing, right? And correspondingly, we're going to have an alternative hypothesis, which represents some kind of Euro or standout stuff, right? Like the lady does have some strong capability or superior capability, which the ordinary people like me doesn't have. Right? So once you have made those hypotheses, we can design experiment. And the experiment could be you just run and pick up set of values, or you do some additional test. In the example just mentioned, right, it's like, okay, the feature, our feature he cooked like 8 cups of tea and with random orders, right? And 4 with milk first and then tea, the other 4 tea first and then milk, right? So you can do whatever experiments you want, right? And based on those experimental outcome, you will have a collection of random samples, and you can calculate some function based on those samples, which we call test statistic t. Remember, this t is still a random variable because it's a function of the random sample from your experiment. Right? And then we're going to choose a significance level alpha. Right? By significance level alpha, it means that, okay, if your statistics t is observation or its value appears to be some rare event, and how rare it is. This is decided by the significance level alpha. Say alpha takes 0.01. It just means like, oh, it possibly means like, okay, your chance you see your statistics is bigger than some alpha, some critical value, should be very low, should be no less than 0. No bigger than 0.01 chance. Right? That is really a rare event. But of course, you don't necessarily every time you're going to choose alpha equals 0.01. You probably choose 0.05, like less than 5%. You still view it as a rare event. That's why we should have some flexibility to set up or choose a significance level alpha. And then you just examine the value of your statistics. And according to the significance level, if the event associated with the value of the statistics has the probability less than or equal to your level alpha, then it is represented or it is called a rare event. And based on this rare event, we're going to reject the null hypothesis. Because again, our intuition is that, okay, in practice, if your H0 is correct, you shouldn't see this rare event in just one experiment. So we're going to reject H0 and we're going to accept H1. So that's the idea of the hypothesis testing process. Question? Okay, great. See you on, let's stop here today and see you on Thursday.